The next presenter, did you know he's one of the two persons in the room that I know of that used to work extensively in the music industry. I kid you not, but he's been hanging out with Whitney Houston, Elton John. I kid you not, this is true story. Please welcome the legendary Dave Coleman.
Can everybody hear me? Okay, and I'm assuming this clicker works. Okay. Okay, so I'm David Coleman, Senior Mobility Leader for Aerohive Networks. Been with Aerohive now about 8 years. I'm CWNE number 4, and that's my Twitter address, so please follow me. I am the co-author of the Cybex CWSP Study Guide. This book came out, the second edition, last year. My two co-authors are Dave Westcott and Brian Harkins. I believe Brian is presenting later today as well. We have one last free copy of that back at the Aerohive booth, so if somebody wants to go grab that, there's one still available. I'm also the co-author of the Cybex CWNA Study Guide, which currently it's the 4th edition. Cybex tells us that it's probably the best-selling book in Wi-Fi in the industry. It sells about 5,000 to 8,000 copies a year. Obviously, a lot of people buy it to study for the exam, but where we've been very honored is that it's taught at a lot of college universities for wireless courses, and it's used as reference guides by wireless professionals all over the world. So it's been very humbling. I can also announce that we are working on the Cybex 5th edition study guide. We've gotten about 6 chapters done so far, and hopefully it'll be available for pre-order on Amazon pretty soon. I'm not going to give you a date yet. Writing books is not easy, and it takes a lot of time. That's my co-author. Now, anybody who's seen me present before, we always do this hashtag, where is Westcott? Because he never shows up to these things. The only way we've ever gotten him to come to one of these events is they had to make him the keynote here last year. And I think they had to bribe him a little bit, too. Westcott's coin operated, so that's why he's not here. Speaking of Westcott, I have a new hashtag. Write the damn book, Westcott. Those 6 chapters that we've written so far, yeah, I've written them. So I'm not going to write this book by myself. So if anybody would like to send that out on Twitter with that hashtag, I would be greatly appreciative. And you all can start hounding him to start getting to work. And just so you know, it's going to be a complete overhaul of the book. We're changing a lot of things around. So I'm actually going to talk about a lot of things today. I'm going to talk about management, control, and data planes. I'm going to talk about the history of the different wireless LAN architectures. I want to talk a little bit about leading into cloud and kind of define what cloud is. And there's actually been several different generations of cloud, and there's a lot of misunderstanding what cloud is. And towards the end of the presentation, too, I'm also going to talk about our APIs and show you some fun things that we've done with our APIs, and that's all tied in with our cloud architecture. And then I'm going to have a special guest for the last 2 minutes to come up here as I wrap up and have a little discussion about 802.11ax. So when you talk about telecommunications, there's 3 logical planes of telecommunications: management, control, and data. The management plane is typically defined by administrative network management or monitoring. So an example of the management plane would be any kind of network management solution that is used to keep track and manage and monitor your routers and switches. Any centralized network management server can be also used to push configurations and firmware upgrades. Now, when you talk about the control plane, you're typically talking about intelligence or the brains of your network, or in most cases, protocols. So if you're talking about a layer 3 routed network, you'd be talking about OSPF or BGP, would be considered control plane intelligence. If you get to a layer 2 network, you can start talking, a control plane intelligence would be considered like the CAM tables on a switch or spanning tree protocol mechanisms. Now, what about these, and then of course the data plane, which is sometimes also known as the user plane. To keep it simple, it's the location of your network where user traffic actually traverses or is forwarded. And that can be a lot of different places. So it could be an individual router where packets are forwarded is an example of the data plane. A switch forwarding an 802.3 Ethernet frame is an example of a data plane. Now, what about these 3 planes in terms of Wi-Fi and wireless? Well, let's talk about the management plane first. Anything to do with wireless LAN configuration, anything to do with monitoring and reporting, that's all management plane, as well as wireless LAN firmware management. Now, what about control plane with wireless networks? Well, that can be a lot of things. It can cover a vast area, including dynamic RF, or RRM as some people like to call it, roaming mechanisms, encryption key distribution, QoS, load balancing, band steering, mesh protocols, application visibility and control. These could all be examples of control plane intelligence in terms of the perspective of an 802.11 wireless LAN. Now, the data plane is, once again, where the data is being forwarded, and it's going to be different depending on the architecture. So a standalone AP handles all data forwarding operations locally, typically, whereas in a wireless LAN controller solution, the data is normally forwarded from to a centralized controller, but data can also be forwarded at the edge of a network by an AP in a controller-based solution. Each vendor has their own unique way and recommendations on how to handle the data forwarding, and there's actually hybrids, and we'll talk about that. So I'm going to quickly go over some of the architectures that we've seen over the years. So in the beginning, there was the autonomous APs, and all 3 planes operated in autonomous APs. So for management, you had to telnet into an AP to configure it. They didn't even have SSH back then, or there was a single GUI interface. Eventually, network management servers started appearing. Anybody remember Cisco Wilsey? Yeah, we're glad that's not around anymore. But it was the first network management server that was used to manage autonomous APs, because otherwise, you had to go and touch every single AP individually. The control plane was also in each AP, and to be honest with you, the APs weren't very smart back then. They didn't have a lot of processing power, so there wasn't a lot of intelligence. And then the data plane, data was forwarded at the edge of the network, despite the lack of widespread support for multiple VLANs at the edge of the network. Now, network management servers were first introduced to essentially manage and monitor legacy autonomous APs, but they can also be used to manage controllers as well. As a matter of fact, we used to use the term a wireless network management solution, but we don't really like to use that. Most people just call them network management servers now, because it might not just be wireless that they're managing. It might be managing switches, VPN gateways, firewalls. Most network management solutions use SNMP to manage and monitor the wireless LAN. Other ones use a protocol called CAPWAP, and there's some other protocols that are actually being looked at by several different vendors. More lightweight protocols, management protocols that you might hear about in the near future. Okay, so network management solutions usually also have extensive diagnostic and troubleshooting capabilities. They can be cloud-based, or they can be on-premises. And I'm going to circle back to the cloud aspect of that in a few minutes. Now, about 15 years ago, the centralized architecture debuted. And that's wireless LAN controllers. And where these three planes operate completely switched around. So basically, all three planes were now put in a central server or a box called a wireless LAN controller. So some of you might remember them being called wireless switches. Does anybody here know who had the first wireless controller? Did somebody say Proxim? That is incorrect. It was Proxim. It was Proxim. Symbol was the second one with their Mobius. But it was called Proxim Harmony. They sold about 5 of them. But then Symbol came out. They did pretty well. And then Aruba and Trapeze and Airspace. And then there was a handful of others. Okay? Now, so the management plane was all centrally, the network management server effectively was in the box. And that was a good thing, because you didn't have to connect to each individual AP. The control plane was also in the box. And that's because the APs back then just didn't have enough processing power. So they built a big brain called a controller, okay, that could handle things like dynamic RF and load balancing and roaming mechanisms. Could they have built an AP with that big a brain? Well, 15 years ago, yes, but the AP would have cost $15,000. So it made more sense back then to put everything into the controller. And then the data plane, all the user traffic was tunneled in a GRE tunnel back to the controller for a lot of different reasons. 802.11 traffic cannot traverse on a wired network by itself, so it has to be encapsulated. Most vendors use GRE. And the main reason that the user traffic was tunneled back to a controller is, quite frankly, there wasn't a lot of support for VLANs at the edge back in those days. Okay? Now, just that being said, that doesn't mean all controllers centralize the data plane. Almost every single vendor will also do local data forwarding as well. But just keep in mind, it just depends on where the control plane intelligence exists. So in some cases, you might lose some of your control plane intelligence if you do the local data forwarding. This architecture is what my company does, and what a lot of other companies are leading towards as well, and that is a distributed architecture. So what Aerohive has done, and has now for 10 years, is we have the management plane in the cloud, and we're going to circle back to that as well, but we push the data plane and the control plane back to the edge of the network. And the control plane is all in protocols with our APs talking to each other. And then the data plane, each AP forwards its data individually and locally, and it is not tunneled. Okay, so once again, the management plane is in a network management server that we call Hive Manager, but the control plane is in protocols with the APs talking to each other. Now, as I'm working on the architecture chapter of the new CWNA study guide, one of the things that I'm going to spend a little bit more time on is this: hybrids. Yeah, we talk about all these different architectures, but I've watched them evolve over the years, and now everybody, and more, there's lots of hybrids. Wireless LAN controller vendors are pushing the control plane intelligence back to the access points. You're seeing that happen more and more. Wireless LAN controller vendors also offer local data forwarding. Distributed AP vendors, like Aerohive, can also centralize the data plane. We can tunnel the user traffic to a central, like ISR router, if so needed. So there's a lot of hybrids. As a matter of fact, control planes sometimes resides in cloud management solutions. So there's a lot of hybrids going on. So a lot of this was, to me, coming to cloud computing. And I just wanted to talk a little bit about cloud computing. And I don't pretend to be an expert. We have a guy named Dan who designs our cloud architecture. And this guy's just brilliant. And I try to spend 30 minutes with him every time I go out to Aerohive just to learn a little bit about what cloud really is. Basically, it's a model that abstracts computing resources and underlying complexity away from the end users. And it should always be available. And with distributed computing models billed as built as the cloud progressed over time from a simple remote server to a more cloud-oriented architecture. And I know that sounds like a bunch of words, so let's get into a little bit more detail. So to tell you the truth, what the cloud first was just a server in a data center. Okay, it was just a server in a data center, but on somebody else's premises in most cases. And that's what most people would call public cloud. The advantage is there's no need to upgrade your hardware. It supported installations. It was basically software as a service, and it was always on, and you can manage multiple distributed sites worldwide. The next generation that we started seeing in cloud was where you had multiple remote machines. So once again, this was residing in somebody else's data center, and it's scalable beyond a single server. It usually had more options, a lot more fault tolerance, and it was all about adding nodes. Okay? And a node, for example, could be an instance of VMware. Okay? Node running on VMware. Now, where we're at today, and when most people talk about cloud, this is what they're talking about. Because those first two generations, if you want to be truthful, were more just about servers. The new generation of cloud is what's called true cloud. That gives you an elastic infrastructure. I'll talk more about elastic in a minute. It gives you infinite scalability. A big part of it is big data. And with things like IoT and 802.11ax on the horizon, the more data you have available, the better. I've heard a lot of talk about comparative analytics. The cloud gives you that, true cloud architecture can give you that kind of capability. It also can be API driven if you can access that big data lake. And there's an eventual goal of machine learning and maybe even artificial intelligence. So Devin, one day maybe you'll have artificial RRM, and I know that'll make you happy. So APIs. All an API is, it's a software interface that exposes the services and data of one application to the programmatic control of another. And so basically APIs are just a way to exchange information between applications and different programs. And it can be done at many different tiers when you have a cloud-based solution. When you talk about, this is the word that to me is the biggest word when you talk about cloud. When somebody starts saying cloud, if they say elastic cloud, that is a true cloud. An elastic cloud allocates resources and networking and processing on demand. And it enables performance availability and scalability. And it can be done manually, it can be done automatically, and it can also be scaled down to decommission resources at a cost saving. So normally when you hear people talk about like Amazon Web Services or Microsoft Azure, that is what they use what is called an elastic cloud. Arrowhive, for example, is currently built on Amazon Web Services, although we are moving to become cloud agnostic here in very soon, so we could actually work on Google Cloud or Microsoft Azure as well. This is actually a very small slide on the Arrowhive cloud architecture. We have a global data center and we have regional data centers. The global data center is simply for users and customers to log in, but all the management and monitoring is done at regional data centers. And each regional data center may have multiple customer networks. We're also moving into an area where if it's a really big company, if they want to have their own regional data center, either on-site at their location or on Amazon's data centers, we can actually give a customer now their own regional data center. And our DevOps team has to turn up and turn it on, but we can actually get a regional data center set up in about 35 minutes. And we're already doing that with some very large customers. When you have a regional data center and you start talking about elastic cloud solutions, it's all about clusters, nodes, and services. And you put nodes, which are basically instances of computers, together into a cluster, and when they can run multiple parallel services. This also builds in lots of redundancy and is constantly and easily scalable, either manually or automatically. Oops, too soon. Can I go back? IoT. So one of the things that our vision is, the work cloud management is going to be even more important, is IoT and the Internet of Things. And here's IoT. Uh-oh. That's IoT. It's the wild, wild west, okay? So there's a lot, you hear it, it's a buzzword, okay? It's here, but then it isn't here. It is continuing to grow. There's been entire standards written for IoT. Currently, right now, though, most of IoT still operates at 2.4 gigahertz. And it is, I'm going to have a guest speaker up here in just a minute to talk about that a little bit more as well. Now, IoT is not just a single device. It's a complete application, security, management, and communication framework. It's not just the physical device. So we've actually, through our cloud-based data lake and our APIs, I wanted to show you a couple of fun things that we've done and some proof of concepts that we've done. We have a guy named Marco Tisler who works for us, and we have an API called the Identity API, and it's strictly for what we call private pre-shared key credentials, where everybody gets a unique pre-shared key, but it's unique and different for every device. So it's the same as, you can have strong PSK security with up to 63 characters, but everybody has a different one. And that also provides identity. It's been a very popular feature at Aerohive for 10 years, and most of our competitors now have similar offerings. Well, one of the things that Marco has put together is a proof of concept, and we're getting some interest in it, using our APIs and with the cooperation of IoT manufacturers. We've come up a way to do zero-touch provisioning and secure provisioning of PPSK credentials onto IoT devices. So we're already talking to some IoT manufacturers that are interested in this. Is Brian Long here? Okay, so I spoke with Brian. He works for a medical device company, and he was telling me what they're seeing in hospitals are that still about 60% of the medical Wi-Fi devices are running a static PSK, and most of them don't support certificates. So it's our view that there's definitely some room for growth in this market using our PPSK credentials in IoT devices, especially if we can make them zero-touch provisioning and auto-provisioning. And we've already got this working. And like I said, it does take some cooperation with the IoT manufacturers, though. So with the power of the cloud and the power of APIs, we've already come up with a proof of concept for auto-provisioning IoT devices. Now I want to show you something else. Internet of Pets. This was something that came up over a lunch meeting, and unfortunately he's not here, but these mock-up slides have been put together by this kid that works for us, Aaron Gates. He's brilliant. He's about 20. I think he was the youngest CWNE for like a week, and then somebody else that was younger became a CWNE. But we at Aerohive have a pet policy where you can bring your dogs to work. And I guess you could bring a snake. So we started thinking, could we design an app where we could have secure credentials for our dogs, but also use our locationing API to keep track of the dogs while they were in our offices. So this is actually something we're working on. It's going to be a reference app. If anybody's interested in our APIs, it's developer.aerohive.com. But this is something that we're doing for fun, but we fully expect to have this out sometime soon. So this is kind of a mock-up of what we're going to build. So you have your little dogs, you flip over the icons, and then you can see where the dog is on the heat maps, as well as information about your dogs, their age, their height, who their owner is. Okay? Wireless info as well, what kind of RSSI, their MAC address. Okay? And then we're going to have little icons, once again, showing you the location of the pets and as they move around. Now, so I'm going to keep moving through the slides a little bit faster. But to do this, we are going to need some sort of chipset. So we are actually working on coming up with a little dog tag device that we're going to be putting on the dogs so that we can then start running our Internet of Pets application. Now, I know this is kind of goofy and fun, but this is just one thing that will show you, with the power of APIs mixed with data that is available in the cloud, the kind of things that you can do. And this is not an official press release on this yet, but when we do release this app for free, we fully expect it to get a lot of marketing press. So the last topic I want to talk about, and I got about 14 minutes, is a little bit about 802.11ax. So I heard it was said that 802.11ax is dead. Well, I'm going to have to disagree with that. 802.11ax just hasn't been born yet, okay? And I will tell you this, Aerohive as a company is going to be very aggressive in terms of 802.11ax next year. The problem with N and AC is they kept introducing new PHY and MAC layer enhancements to give us higher data rates. We built bigger highways, and we built faster cars. But this is the problem, okay? So the highways are full, and they're congested. And it's just a big traffic mess, okay? This is the solution. We need better traffic management. So everybody's probably seen me with this slide before. Everybody knows that RF is a half duplex medium. At any given time, only one radio can transmit on a frequency domain or a channel. Everybody takes turns. Now, data rates, hopefully most of the people in this room understand this, but data rates are not the same thing as TCP throughput. The medium contention protocol that you learn about when you take CWMP training, carrier sense multiple access collision avoidance, consumes much of the available bandwidth for whatever the data rate is. Aggregate TCP throughput in a legacy ABG environment is about 40 to 50% of data rate, and that's in ideal conditions. With AC and N, it got better. With N and AC, you could get 60 to 70% of the data rate in ideal conditions. But the key to that is ideal conditions, like a Faraday cage. Because the efficiency of the MAC sublayer always drops as you add more client stations. And you get increases in collisions, and you get more medium contention overhead. So the higher data rates have not been the answer. More and more, we're getting this higher density of clients. And then the bulk of data frames that are actually transmitted, 75 to 80% of them are small and under 256 bytes, which means that's going to result in the overhead at the MAC layer and medium contention overhead for each one of those small frames. So that's what 802.11ax is all about. 802.11ax is the high efficiency standard. It's going to use PHY and MAC layer enhancements for better traffic management. Now, the goal is to increase the average throughput 4 times per user in a high density solutions. And it operates in both in 2.4 and 5 gigahertz, not just 5 gigahertz like AC does. So what is new? I'm not going to go over all these things in great detail, because the main thing it's going to be about, especially in the first generation of chipsets, is OFDMA. It's a better use of the frequency space. But there are some other things. There's something called BSS coloring that sounds interesting, but you're not going to see it in the first wave of chipsets. they're talking about uplink multi-user MIMO. Look, we all thought downlink multi-user MIMO was going to be the really great, and how'd that work out? So I'm not holding my breath for that as well. And then they're even talking about 102.4 QAM modulation, which means you'll have to be standing 1 foot away from the access point. There's some more comparisons of the different technologies right here. So 802, once again, you'll see the main goal was not to increase data rates. It's more about a better efficiency, okay? But there is a change in frequency multiplexing, mainly what I'm going to talk about, I think, in the next slide or two, OFDMA. So if you look at traditional OFDM channel, an AG in or an AC, and let's just say your channel width is 20 megahertz, and there's all your subcarriers. When a radio is transmitting, he's eating up that whole 20 megahertz channel. And then when client 2 transmits, he's eating up that whole channel. And then when client 3 transmits, that whole channel on and on and on and on. The problem is, we hear about 40 megahertz channels and 80 megahertz channels. In reality, smaller channels are better. Or I like to call them baby channels. And that's what OFDMA is all about. It's a better use of channel reuse, where bottom line is you could do this. Let me go back. What if you could split up that 20 megahertz channels, and then 2 of them into 2 10 megahertz channels, and 2 clients could be, the AP could transmit to 2 clients at the same time. Or maybe 4 clients at 5 megahertz. Remember I said most of the frames are really small. You don't need the whole 20 megahertz channel, let alone an 80 megahertz channel, which we all know is kind of a fantasy. So this is, and these are called resource units. And there's all kinds of different resource units and different sizes that are being defined by the AX standard, okay? And this is going to be the main thing that is going to make AX more efficient. It's a better use of the channel frequency space. Now, here's, to me, the biggest change of all. The AP controls the medium for both downlink and uplink frame by frame. And the AP can adjust power per resource unit. There's also the number of these subchannels, these resource units can change and vary on a packet per packet basis. And the AP decides how client stations transmit on the uplink. Now they will have to be AX for that to work, okay? But this has never really happened in this industry. Synchronizing uplink transmissions, unless you want to have Devin teach you PCF again. But this is a big system exchange. I can say this, I mentioned Aerohive is going to be very aggressive in terms of coming out with APs next year that are AX. And from what we hear from the client chip side vendors, they're also going to be very aggressive. And so that you will see AX clients a lot faster than you think. So it is optimized for other environments too. There's some other enhancements to design for outdoor networks and long distance range. There's complete changes. There's new PHY headers. But what I mainly want you to get out of this conversation is where all the technology that's coming is going to be the new use of OFDMA. And for me personally, I've been in the industry now for about, I don't know, since, when did I start? 1999. To me, this is one of the most excited that I've been about a new Wi-Fi technology in a long time. Probably the one that I was most excited about before was 802.11n, when I had to completely teach myself Wi-Fi over again. So I think there's going to be, when AX starts coming out, we're going to have to start thinking about redesigning our networks, okay? But it's not just going to be necessarily ripping down an old AP and putting up a new one. And it is, of course, going to require clients as well. And so vendors that are smart are going to do things like maybe they can have settings that are AX only, because there still has to be backwards compatibility with the other clients. And you know what the backwards compatibility means, right? RTS, CTS. And you know what RTS, CTS does? It's overhead. So I think you'll see vendors do things where there might be a checkbox where it's an AX-only radio, and there's manipulations at the MAC layer that can achieve that. Another big thing that's being added is new power save mechanisms. And it's specifically for IoT devices and saving battery life for IoT devices, and this is actually going to be part of the AX standard. And I'd like to invite somebody else up here on stage real quick to talk about the next couple of slides. And Perry Carell, are you in the room? So everybody, this is Perry Carell. He's a recent hire. He's been around forever. Perry is our rep to the Wi-Fi Alliance and the IEEE.
Thank you, David. The reason I'm up here is because last week I got a presentation at Wireless LAN Pros in Lisbon where I kind of stirred the pot a little bit about saying 2.4 is not dead. Oop, okay, wrong one.
Just the clicker. The green one.
I went back and I looked over the last 3 or 4 years, and the good thing about the internet is everything's always there. The bad thing about the internet is everything is always there. So I was nice enough to take out the names of the people who put these quotes up there for the good and the internet. And it's like Wi-Fi is dead, you've got to kill it, it's going to go away. Or 2.4 rather is dead, it's going to kill it, it's going to go. It's not. It absolutely, we're all going to die. 2.4 isn't. 200 years from now, 802.11 VK is probably going to be using the 2.4 band. Because that's what it is. 2.4 is not a dead technology, it's not token ring. It's not an evil protocol, it's not SNA. It's a frequency. It's 83 megahertz of bandwidth. That's all it is. And saying there's something wrong with it, you know, we saw a couple slides over the last couple days that we're dying to get, you know, Uni 4, an extra 75 megahertz, we really need that. Or Uni 2B, an extra 125 megahertz, we really need that. And we're ready to throw this away. It's not going anywhere. It's an important thing to understand. It's a usable frequency. Is it tough to use? Absolutely. I'm going to give you a story. One of my favorite hotels when I come back from Europe is, I won't mention the name of the hotel, but it's near Terminal 4. 10 years ago when I was there, it was 2.4 G only. Last Saturday when I was there, it was 2.4 G only. And this is a secret, don't tell anybody, it works. When I set up my phone with T-Mobile with Wi-Fi, it worked. Skype, it worked. And I asked the manager about 2 years ago, why are you still using this? He goes, you know, every week, every month, I get somebody comes up to me and say, why are you using this old technology? And he goes, the only people that complain about that are IT people. And when enough regular people complain about it, I'm going to change. But this all came out when, obviously, 11AC came out, and it's like the final knife in the back of 2.4. It didn't go away anywhere. Now, a couple years later, shouldn't give up on the 2.4 yet. Enough already. It's not going away. It's not dying. When I was getting ready to do this, I was kind of actually talking to some of our chip manufacturers. And they're saying, you know, there's a couple brand new manufacturers in China that are kicking out boatloads of 11N, 2.4 only technology, and they're shipping them over here. And why? Make yourself, you're a product manager for an IoT company. You're making a widget, you're making a sensor, you're making something, and you want to sell 1 million of these. So what do you want? You want the cheapest thing possible. So I'm going to get a really, really cheap 2.4 only 11N chipset. I don't care about gigabits. I don't even care about megabits. Kilobits is probably good enough for me for what I'm trying to do. Also, the next thing, I want low power. Give me one radio, give me 1 or 2 streams. That's all I want. Give me great propagation. That's 2.4. Give me great penetration to a wall. That's 2.4. Give me something I can use anywhere in the world. That's 2.4. I'm not saying 2.4 is going to come back and replace anything. I'm just saying it's not dying. So if you talk to anybody today or tomorrow, whatever, and they say, yeah, 2.4 is dead, say, well, thank you very much, have a good day. You're going to die, but it ain't. You know, and that's the important thing to understand. It's just a frequency. Is it tough to use? Yes, but that's why you guys are here. If Wi-Fi was easy, anybody can do it. You know, you've seen some unique things you can do. I mean, you actually have more flexibility because you can be an idiot with it. But once again, the hotel I was at, they had 2.4 and it worked great. The hotel we were at Wireless LAN Pros, they were using every channel and stuff. And that's the important thing, the final thing to think about. If you look at a network, and I've been in this a long time, if you look at a Wi-Fi network, a 2.4 network, and you see them using more than 1, 6, and 11, There's a 95% chance they don't know what the hell they're doing. But there's also a 5% chance they do, because you can do some neat things with it. Thanks, that's all I got.
All right.
Questions? 2.4 is great, right? And anybody who doesn't believe me, slowly raise your left arm and look at that 2.4 only device there.
All right. All right, so thank you, Perry. I want to thank everybody here. Thanks everybody who has ever bought a copy of my book. I make $1 every time you do that. So that helped put my kids through colleges, and it's been very humbling. And thank you, CWMP, for having me. So thanks, everybody.